In a previous video, we had a person walking on an escalator, and both the escalator and the person were going east. We wanted to determine the resultant of that person while that person was walking on the escalator in the same direction the escalator was moving. We ended up getting a resultant of 7.98 miles per hour going east of that person relative to somebody watching that person move on the escalator if that person watching was on the ground. But now we're going to do another part. Do a part B. What if the person was walking in the opposite direction that the escalator was going? So now what we have the escalator. The escalator is still traveling 4.50 miles per hour east. But now the person is walking in the opposite direction. The velocity of the person is 3.50 miles per hour, and this person is going west. The escalator is going east, whereas in this previous problem they're both going east. We're going to do the same problem except they're going opposite directions. So all our conversions, we're going to use the same scale. 1.00 centimeters equals 1.00 miles per hour. So the conversions stay the same. And so now all we need to do is add the vectors. They're just going in opposite directions. So what I'm going to do, doesn't matter what vector you add first. Since I started with the velocity of the escalator first in the previous problem, I'm going to draw the velocity of the escalator in this problem. So I'm going to start right here. And the velocity of the escalator is going to be 4.50 centimeters for the magnitude of the vector, and that vector is going east. So again, I draw this on here, 4.50 centimeters. Is going to be here. Draw that to that point. Now make sure you see that line and use my arrows to make sure we draw that magnitude correctly. So this is the velocity of the escalator, which is 4.50 miles per hour going east. We then add the velocity of the person, and again, since it's a one-to-one scale, we're using 3.5 centimeters for the magnitude or length of the vector of the person, but now that person is going west. We still add vectors tail to tip, so I'm going to take the tail of this 3.50 centimeter length vector, put it at the tip of the first vector I drew, and draw it in the direction west of the correct magnitude. And that magnitude is going to be 3.50 centimeters. So if I put this right on top of there and go 3.50 centimeters, I'm going to be at this point here. I'm going to draw that vector, and technically it should be directly on top of it. I'm going to draw it just a little bit above it so you can actually see that. And so now this is the velocity of the person, and that velocity is 3.50 miles per hour, and the vector is pointed west. And so now what we're going to do is, so we've done these steps. We've identified the vectors, identified the scale. We did the same scale previously. The conversions were already done. We added the vectors tail to tip. We now draw and measure the resultant vector. The resultant vector is always drawn from the tail of the first vector to the tip of the last vector added, which is from here to here. I'm going to draw and measure that vector with my 0 point on there. And I'm going to draw it to the tip of this vector so we can see that. And this is what we call the resultant velocity. The resultant velocity, I'm going to measure the length of that vector. Now if I measure the length of that vector, let's see if we can zoom in a little bit here. And that's real close to, I'm going to say this is not quite on the 1. Let's say it's 0.99. This is going to be 0.99 centimeters. I then need to convert that using my scale, and it's going to be 1.00 miles per hour for 1.00 centimeters. We end up getting 0.99 miles per hour. That's the magnitude of the vector. Remember, we have to use the scale conversion to get the magnitude, but now we have to also measure the angle and identify the direction. So the angle is pretty easy because this vector is pointing due east, and so the resultant is east, 0.99 miles per hour due east. So you can see that we have similar processes for adding vectors. They're tail to tip. The only difference is both these vectors are in the same direction. In this case, the vectors were in opposite directions, but we always add vectors tail to tip, keeping the length or magnitude and the direction constant.